Hello everyone. Today we're going to talk about interaction diagram in reinforced concrete column. That is combination of steel and concrete and works under compression in general, but we may have just tension as well. So first we're going to discuss about 3D view, and for simplicity we will discuss on 2D view and eccentricity from just one axis. So in 3D view, you see that we have a section. It can be any shape, just as long as we can define the center of the section. We can have this concept. So we have a P compression load with eccentricity from EX and EZ from this coordination system. So we will have P at the center if we transfer P to the center, and then we will have effect of that eccentricity that comes as bending moments, and for EZ will be PEZ, and for EX will be PEX, bending moments on Z and X, about Z and X axis. So let's go talk about 2D. For simplicity, we have a section and we have a P with eccentricity of E. So it will be equivalent to P at the center, the same value, but we will have bending effect of that load and eccentricity that comes PE. So the section will be under 1P at the center and bending moment that applies tension on one side and compression on other side. So you know what is interaction diagram? It is just the interaction between M and P in a section. It is general shape, but we always use reduced area to compare with the applied load. If we have a section, a concrete section, that is P star, and it will be P star for design load, that is factored load, like the combination of loads like 1.2G, 1.5Q, or 1.35G, and all together, after all, we will have P star or design load with eccentricity of E that will give M star. If combination of P star and M star falls in this green area, it means that we have safe design. Otherwise, it means that the section cannot take the load combinations, the combination of P star and M star. We need to decrease the load, decrease eccentricity, or strengthen the section or increase the section capacity. And one thing, just remember, we are talking about section, not the length. We will talk later. Just when we talk about later, we will have another criteria as buckling load that will be compared with the compression load, and whichever is lower, it will be applicable. So let's go to discuss about drawing this interaction diagram. How are we going to draw interaction diagram? To draw interaction diagram, in general, we have 4 points as A, B, C, D, and we have 2 axes as P for compression and M for bending. And this is the general shape for and reinforcement arrangement in a section. It is plan view. A is P node or squash load or pure compression. It means that we don't have any eccentricity, and M due to eccentricity is 0. So the whole section is under pure strain distribution or just uniform strain distribution. Just remember, it is strain distribution, not stress distribution. So we may have, based on ES value or modulus of elasticity, we will have different stress values in concrete and steel parts. But for strain, all are same values. To calculate this one, you will need alpha 1 and alpha 2 values. That has different values in different codes of practice, but anyway, it is much easier to follow the code to calculate this P node. Second point is decompression point. Point B here is decompression point. We have P, but this time we have some eccentricity from the center, and it provides P at the center, and M is equal to PE about the center. But still, whole section is under compression. It means that still on this area, still on the other area, and all still are in tension, are in compression, and concrete is completely under compression. But the extreme point for tension is zero strain. It means that it is going to tension zone, but still is under compression. This is strain distribution starting from 0 to maximum for concrete, that is 0.003 in general. And we can calculate strain value for steel layers that we have here. If you follow the section, we have 1, 2, 3, 4 layers of reinforcement, so we may have just 4 layers of strain for reinforcement, and we may have just some, especially for this one, we may have just yield reinforcement for this one, but still it's okay to calculate, and based on strain values we can calculate for linear distribution of strain here, and we can calculate the loads on each element of reinforcement bars and compression side. Part C or point C is balanced failure point. It means that one side is in compression, the other side is in tension, but tension reinforcement failure and compression concrete failure happens at the same time. We have P with eccentricity from the center. In this case, we will call it E balance or EB, and it will provide P balance and M balance at the center. M balance will be PB, EB. This one is very special case, and it is much easier to calculate because you don't need to assume yielding of reinforcement and checking that. Just from the first point, we know that the reinforcement has yielded at the extreme point, and concrete on the compression side has yielded as well. So we have just linear strain distribution here, and D for tension reinforcement, and DN at the balance point for compression side, or just about the neutral axis. So we can have strain values for each layer of reinforcement, and we can calculate the load on each reinforcement. The last point here, the last point in this diagram is D. D is M node or pure bending. Pure bending means that we don't have any compression load. We have just one bending load. It can be just couple action of point loads in E distance from each other, and P minus P is 0 point load, but it gives P times E bending effect. And we have tension bar at tension side and compression bar at compression side, and also compression part of concrete after neutral axis. So you know how to calculate this bending capacity. We will have D, Dn, and we have strain distribution that is always linear, and we can calculate, we can assume that strain is yielded, and we can go to N to check Dn and Dm value, then we can have just another back calculation to check if our assumption is correct or not, and it is easy to find this m value. Just remember, always we're going to use reduced capacity of m. If we calculate mn, we're going to apply phi value or reduction factor value, that is combination of ductility factor, and then we're going to use that to compare with the design loads. That's it for today, and just in the next video we will talk about P node or squash load and buckling load, how they are compared, and also ductile and brittle failure in reinforced concrete section. That you will see that it is very easy to define if the section is failing as ductile section or tension control section or brittle or compression control section. It is much easier to use interaction diagram to say if the applied loads cause ductile or brittle failure in the section. Thanks for watching. See you next time.